Hello, welcome to my channel. Before proceeding to study, please subscribe to my channel. Today, we will explore the fascinating world of basic electrical and electronics engineering. We'll dive into key concepts like general construction, working principle, e.m.f. equation. Slide 1. General construction of a single-phase transformer. Let's begin with the construction of a single-phase transformer. A transformer is a static electrical device that transfers energy from one AC circuit to another using magnetic coupling. It consists of several key components. 1. Core. This is the central part of the transformer and is made of laminated soft iron. Laminations reduce eddy current losses. The core serves as a low-resistance path for magnetic flux. 2. Primary winding. This is the coil where we connect the input AC voltage. It produces a magnetic field when current flows through it. 3. Secondary winding. This coil is where the transformed voltage is obtained. Depending on the number of turns, the voltage can be stepped up or down. 4. Laminations. These are thin insulated steel sheets stacked together to form the core. Laminating the core reduces energy lost due to eddy currents. 5. Insulation. The windings are insulated using materials like varnish or paper to prevent short circuits and ensure safe operation. 6. Tank or enclosure. In large transformers, all parts are housed in a tank filled with insulating oil, which also helps in cooling. 7. Bushings. These are the terminals where the windings connect to external wires. They are well insulated to handle high voltages. 8. Cooling arrangement. Transformers get hot during operation. To keep them from overheating, we use oil, fans, or radiators for cooling. 9. Example, a mobile charger uses a small step-down transformer to convert 230 volts AC to around 5 volts DC after rectification. So in summary, the transformer is carefully built to efficiently transfer energy while minimizing losses and ensuring electrical safety. Slide 2. Working principle of a single-phase transformer. Now let's understand how a transformer works. 1. The transformer operates on the principle of mutual induction. This means when the magnetic field created by one coil, primary, varies, it induces a voltage in the other coil, secondary, placed nearby. 2. When alternating current, AC, is supplied to the primary winding, it produces a changing magnetic field. This magnetic flux flows through the iron core. 3. This alternating magnetic flux links to the secondary winding through the magnetic core. 4. According to Faraday's law of electromagnetic induction, a changing magnetic field induces an e.m.f, electromotive force, in the secondary winding. 5. Importantly, there is no direct electrical connection between the two windings. The energy is transferred purely through the magnetic field. 6. The voltage in the secondary depends on the number of turns in the coil. More turns in secondary equals step-up transformer, increases voltage. Fewer turns in secondary equals step-down transformer, reduces voltage. 7. Efficiency is very high in transformers, typically above 95%, especially in power distribution. 8. The direction of the induced e.m.f is governed by Lenz's law, which states that the induced e.m.f will oppose the change in magnetic flux that caused it. 9. Example, your laptop adapter uses this principle to deliver the appropriate voltage safely from the wall socket. Slide 3. e.m.f. Equation of transformer. Let's now discuss the e.m.f equation, which helps us calculate the induced voltage in the transformer windings. 1. The standard e.m.f equation of a transformer is A equals 4.44 times F times N times phi max, where A equals RMS value of induced e.m.f, F equals frequency of supply in Hz, N equals number of turns in the coil, phi max equals maximum flux in Webers. 2. This equation is derived from Faraday's law, which relates the rate of change of flux to induced voltage. 3. In a transformer, primary e.m.f. A equals 4.44 times F times N times phi max. Secondary e.m.f. A equals 4.44 times F times N times phi max. 4. The turns ratio defines how voltage is transformed. A equals N. If N greater than N, right pointing arrow step up. If N less than N, right pointing arrow step down. 5. This formula assumes ideal conditions, no core loss or leakage. 6. No load condition means the transformer is energized but there is no load connected to secondary. In this case, the voltage ratio equals the turn ratio. 7. Example problem. Suppose N equals 1000 turns. N equals 100 turns. Phi max equals 0.01 Weber. F equals 50 Hz. Then, A equals 4.44 times 50 times 100 times 0.01 equals 22.2 volts. This shows how we can use the formula to design or verify transformer performance. Understanding this equation is essential because it directly connects physical design, turns and flux, to the output voltage we want.